Swayam Prabha. Digital India. Educated India.
We have now constructed the set E. Okay. Now what? This is the slightly complicated part. Everybody has trouble with doing this part of the Salle invariance, is to find the set M. Okay, and M has to be invariant and inside E, and it is the largest invariant set. Okay, can't be anything. Cannot be any invariant set larger than this. Okay. Now, how do we do this how do we usually do this? I mean, because I don't know how to find the largest and smallest, right? I mean, it's not like an optimization problem that I find largest and smallest, because you can see that these will be very complicated sets. Yeah, this kind of optimization will be virtually impossible to do. Basically, you will not find an engine which will solve this optimization problem if I actually thought of finding the largest invariant set and all, because you will have to initialize, you will have to take all initial conditions and try to do something. Okay, not possible, not possible. So what I will do is, what everybody does, not what I will do. Yeah, what everybody does is assume E is invariant. Okay, so we actually assume that E is itself an invariant set. Okay, so this sort of helps us continue forward. What does it mean if E is invariant? Okay, what do you need for E to be invariant? It means if I start inside E, I must remain inside E. But look at the interesting thing. What is the set E? Is this guy. Okay, alright, it is this guy. Now the first term is a continuous, could be a continuous quantity, right? It can take any value between minus 2 pi to 2 pi. Notice, this guy can take any value between minus 2 pi to 2 pi. So I can't really conclude too much about this, but what we use is the fact that the second term, that is x2, has to be 0, is fixed. So for me to be invariant and to remain inside E, I need x2 to be identically 0 for all E in this case. Yeah, I need x2 to be identically 0. And what does this mean? If something is 0 forever or some constant forever, and all these are continuous, right? x1, x2 is continuous because I have a differential equation, right? So obviously continuous, nice properties. So what does it mean? If x2 is 0 for all time or any constant for all time? No, not really, right? That would mean all states are 0. Only one state being 0 is not equilibrium. Just like you know that alpha comma 0 is not an equilibrium, right? I hope you understand that any x1 is not the equilibrium. Otherwise it would be this 0 velocity, 0 velocity, 0 velocity, all these will be equilibrium. So this is not an equilibrium. No. What can I say? If any quantity is, if any function is the constant function, what do we know about the function? This is a function of time, right? I mean, although I write it like this, it's actually a function of time. Then x2 dot is identically 0. Yeah, x2 dot has to be identically. That's the only way a function can be a constant function. Alright, which means what? What is x2 dot? Anybody remember? This minus k sine x1 minus c x2. This has to be identically 0. All of this to make E invariant. All of this is to make the set E invariant. Without this happening, set E cannot be made invariant. Okay. Now I already know that this guy is already going to 0, right, and the left hand side is already 0. So what do I know? What do I conclude? This also has to converge to 0, not converge to 0, whatever, has to be 0. Okay, has to be 0. And what do I know? Sin x1 is equal to 0 at what? X1 equal to what? N pi, right. So 0, pi, I will not write 2 pi because after that it is repetitions, right. I will just write 0 and pi, and you see 0 and pi are both in our set omega, right, both in our set omega. So we started by assuming that E is the invariant set, but to ensure that E is in fact invariant, I required sin x1 to be 0, which gave me exactly 2 values, not all of E, not all of E, okay, everything else is the same, right, 0 and pi, all other angles are the same. You can write them if you want, but yeah, you can write 0 and pi. I know 2 pi is also there, but it's all the same, so I am not including them. So what do I have? I have that the invariant set is what? M is equal to what now? What is the set M now? 0, 0 and pi 0, okay, alright. Just by starting with E being invariant, I have concluded that only these 2 points constitute the invariant set, okay. So M is the invariant set, the largest invariant set. You cannot have anything more. Why? Because I started with E being invariant, which is the largest set I had to work with. From there I could only get out that these 2 points give invariance. And what are these points? These are exactly the this and this. So what does Lasalle invariance say? Because I have satisfied all the requirements of the Lasalle invariance, I constructed a compact invariant omega, right. I had a V and a V positive semi-definite, V dot negative semi-definite in omega. In fact, it is in D, but in omega also, okay. And so, and then I constructed the E and the M sets. So I have satisfied all the requirements of the Lasalle invariance principle. So Lasalle invariance principle says that if I start in this set omega, not anywhere in the domain, if I start in this set omega, okay, then I will converge to this, okay. So interestingly, what I have been able to prove is still not if you say everything, because although there is no restriction on the angle, right, it says if you start in omega, okay. So I can start at any angle because minus 2 pi to 2 pi closed set includes all the angles, no problem, okay. And it says I will converge to either this point or this point, it does not specify which point, you can converge here or here, no problem. But the velocity is restricted, there is a restriction in the velocity, although again in reality you know what, I can start at any velocity theoretically and I will converge to an equilibrium, one of the two equilibrium for a pendulum, okay. In fact, I will converge to this equilibrium only, I will never converge to this equilibrium. If the velocity is anything but 0, I will converge to this equilibrium only, okay. So in fact, any velocity is allowed in reality, but I have only been able to prove this much, okay. So there is a caveat, okay. I mean, even Lasalle invariance does not let us prove what we know in reality, but this is more than enough because I can choose any c. If you give me velocity 1e power 6, I will choose a c accordingly and tell you, yeah, this will work, yeah, because all I have to do is c was nothing, c is just a artifact of our imagination, so c is nothing, we created it, So, if you give me 1 e to the power 6, 1 e to the power 10 velocity, for whatever reason you want to put a rocket thruster on the pendulum, but you will, I can still guarantee that you will converge to the equilibrium by choosing a large enough c. Okay. But yeah, in theory, once you fix a c, your velocities are bounded, yeah, not unbounded velocities. Unbounded velocities are not okay, which is obviously fair enough, for all intents and purposes. Okay. So, do you all understand how to use the LaSalle invariance? I have also asked the TS to try some examples. I hope they try something other than the pendulum. Anyway, with LaSalle invariance, application of the general LaSalle invariance with multiple equilibrium. Okay. So, it is important that we follow this. Now, I also want to state, if you have no questions on this, I want to state the stability versions of these theorems. Okay. So, LaSalle invariance was obviously by LaSalle, yeah, but then the stability versions of these theorems were almost parallelly developed by Krasovsky-Barbashine. Okay. So, therefore, I like to call it Krasovsky-Barbashine-LaSalle theorems. Some books call it Krasovsky-LaSalle, some call it Barbashine-LaSalle, but whatever, it is better to put all the names. So, these are very close to LaSalle theorems, but they only deal with stability of the zero equilibrium. Okay. Here you have a general multi-stability, what you can call multi-stability, because multiple points you can reach a limit set, yeah. Here you specialize to reaching the origin only, yeah. And how do we do that? We no longer start with V which is only positive semi-definite. We actually start with a proper Lyapunov candidate. Okay, this is now a proper Lyapunov candidate. It is positive definite in C1, and we just have semi-definiteness on the V dot. Such Lyapunov candidates are called non-strict Lyapunov functions. Okay, for all x in D, notice for all x in D, not in any omega. You see that the omega is carefully missing here, there is no omega here. Why? Because I know that I can construct a omega just by this fact, we just did in the example. And then if I define the S, similarly whatever we called E here is the S here, just because it is a stability theorem, so I am using a different notation, that is all. If you define the S as such, and if x equal to 0 is the only invariant trajectory in S, this is just wording that some texts use, but this is the same as saying the set x equal to 0 is the largest invariant set inside S, then x equal to 0 is asymptotically stable. Okay. On the other, and then you can also state a global version which says that if now you do not have a domain, you have all of Rn, okay, again negative semi-definite in all of Rn, and you have the same things happening, then you have global asymptotic stability. Okay, that is it. If the domain goes away, then you have global asymptotic stability. Okay. Notice all these results, LaSalle invariance, Barbashine, Krasovsky, LaSalle, all these are only for time invariant systems or autonomous systems. Okay. For time varying systems, the results are significantly more complicated. Okay. I mean, not easy to apply these results. Okay. Because the notions of limit points and limit sets itself becomes very messy. Okay. All right. So, these are the stability versions of the theorems. All right. Now, if you go back to our example, how would I do the stability version? I am, in fact, this is actually pretty straightforward. Yeah. What will I do? I will no longer take minus 2 pi to 2 pi. I will just take minus pi to pi, because I only want the bottom equilibrium included in the set now, because I am looking to do stability of 0 equilibrium. So, I will not include the top equilibrium in my set D. Okay. So, my set D will now contain only minus pi to pi. Okay. Anyway, this is something I will ask you to complete. Yeah. But the rest of the steps are exactly the same. You still have a V. Okay. Notice that as soon as I choose x1 in minus pi to pi, this is positive definite. This we discussed, right? Earlier in the example, we did this example, okay? If x1 is in the minus pi to pi range, not minus 2 pi to 2 pi range, in the minus pi to pi range, this is a positive definite function, right? I hope you all agree, yes? Because this function will not be 0 anywhere but at 0, 0. The problem with the larger range is 2 pi is included, then it is not positive definite. But if 2 pi is not included, so minus pi to pi, then 0 is the only point, that is x1 equal to 0 is the only point where this can become 0, yeah, x1 x2 equal to 0, nowhere else, okay. So the only difference is in the domain, okay. So it will become minus pi to pi cross r. After that it is very straightforward. V is positive definite, V dot is negative semi definite in the domain, okay, and after that this same analysis goes through it. This analysis is not changing. The set E, or in this case the set S, whatever you can call it S, but this is going to be exactly the same, right, because V dot is exactly the same. So this set is the same. If this set is the same, the set M is the same without this guy, because minus pi to pi does not contain pi at all. Minus pi to pi open set, remember we took for this domain is minus pi comma pi, okay. For applying the Barbashine-Krasovsky-Lassalle, we take this. So this is not even part of this set, okay. So M contains only the origin, M contains only the origin, okay. All this, so nothing changed in the analysis. I just shortened my or reduced the size of my domain, and just by reducing the size of my domain, instead of applying the general Lassalle principle, I am applying the Barbashine-Krasovsky-Lassalle. Why? Because by shrinking the domain, I removed this equilibrium. Minus pi to pi does not contain this guy, yeah, because I excluded pi, okay, that is all. So by shrinking, so what am I doing by saying minus pi to pi? It is starting from here and here. So it is like it goes from here all the way to slightly here, that is it. Minus pi to pi is just everything but that vertical, upward vertical line, okay. So I have essentially taken everything but that top vertical line, and so I have skipped the second equilibrium. Once I skip the second equilibrium, there is only one equilibrium, okay. And remember, I always told you, when you have one equilibrium, only then you can talk about, you know, stability or global stability. If you have multiple equilibria, then you have to think Lassalle type ideas. So that is all. I shrunk the domain so that I have one equilibrium in this domain, and then applying Barbashine-Krasovsky-Lassalle is very easy, because the set E remains the same and the set M contains only the 0 equilibrium, and that is proof that 0 is asymptotically stable, not global because of this restriction in the domain, is not global, but whatever, it is asymptotically stable, more than enough, okay. And this is in fact sounds more general. I did not have to do all this omega construction and all, right. It gave me asymptotic stability. So basically what it is saying is, if you start anywhere but at this equilibrium, anywhere but this equilibrium, so you can start anywhere arbitrarily close to it but away from that equilibrium, then you will fall here, which is what is the reality also, right. You can verify that very easily in experiments, alright. Is that clear? Okay. The spring mass damper example is also very similar and much easier. This is a spring mass damper is just a linear version of the pendulum, linearized pendulum if you may. This is what the dynamics looks like. X1 dot is x2, x2 dot is minus k1 x1 minus k2 x2. The constants k1 and k2 depend on yeah, spring mass coefficients, alright. And what do? I take V as the energy, right. This is the, what is this term? Potential energy. Potential energy, this is the spring energy, energy stored in the spring, this guy, and this is the kinetic energy term, okay. Spring energy, potential energy, kinetic energy. If you take the derivative, and of course you can see that this is all nice and radially unbounded, in fact, V is radially unbounded. I hope that is clear to you. Yeah, this is, yeah, in fact in all of Rn, the domain, you do not even have to worry about the domain here, sorry, all of R2, okay. This is, V is valid in all of R2, V dot is negative semi-definite in all of R2, and V is radially unbounded in all of R2, okay. So, once you have that, it is again the same kind of S construction, right, because sorry, again E has been used, it does not matter. So, what is the set E now? The set E is just V dot equal to 0, which is the same, amazing, no? It comes out to be exactly the same. You just need x1 comma 0, all sets of the form x1 comma 0, okay. Now, I know 0 has to remain, you have to, the second variable or x2 has to remain at 0 for all time, therefore, x2 dot has to remain at 0 for all time, which means that minus k1 x1 minus k2 x2 has to be 0 for all time, same logic, but x2 is already 0, so x1 also has to be 0 for all time. So, what is the largest invariant set? In E, x2 was already 0, now I also want x1 to be 0. So, 0 0 is the only invariant set inside this, okay. From every other point you will move, okay. So, they are not invariant sets, okay. You cannot find any other invariant set. So, this is the largest invariant set inside E, okay. So, this is in fact your whatever M set, if you may, yeah. And so, any trajectory which starts anywhere, in fact, will converge to this 0 0 equilibrium, okay. Again, it is a linear system, you could have very well computed the eigenvalues and obviously found out that they were negative, and you would have concluded exponential stability. This is just giving you an alternate way, but this is just a way of using this theorem, that is all. I mean, you have already seen that I can use it for nonlinear systems also. In fact, you can use it, Salle invariance, like I said, is a method of choice for typically for geometers, because like I said, because they like to use the energy as the Lyapunov candidate, and whenever you use the energy of the as a Lyapunov candidate for these conservative type systems, that is with no external forces, invariably your V dot will be 0, right, because energy is conserved, right. It will not be less than equal to anything else, it will be exactly 0, and from there if you want to conclude anything, you have to use Salle invariance, okay. You have no choice but to use Salle invariance, okay. So, Salle invariance is a very strong method, yeah. I am not sure if we will have time, but there is also what adaptive control folks use is the notion of Barbalat's lemma. It is a different way of doing this Barbachine-Krasov-Lassalle, okay, which is more, I would say, you might find it easier to use, and it can be used for time varying systems also, okay. Here you can't, yeah, you can't use these for time varying systems, these results in this form. But Barbalat's lemma also cannot be used for multiple equilibria case. So, the general Lassalle invariance principle is a very powerful result, yeah, it is a very strong result. You can't get multiple equilibria type results from typically any other method, okay, not easy. You have Poincaré-Benedictson theorem and all that, but not easy, they have all sorts of interesting assumptions which you may not satisfy, yeah. So, Lassalle invariance is actually a very powerful tool that way, yeah.